Hello everybody. In this video we are going to develop a custom Aruco marker detector. Now you may ask yourself why develop a custom detector when OpenCV already has a built-in Aruco marker detector because it's fun and it's a very good practice for some basic image processing. So let's do it. If you are not familiar with a Aruco marker, so this is an example of some Aruco marker. It's a marker that is relatively easy to detect, and it can be used in augmented reality applications when we want to estimate the location of the camera. So one property of this marker is that the pattern is unique on all orientations. So when the camera is here, we have some pattern of the marker, and if the camera moves here, the Aruco marker has a different pattern, and if the camera moves here, the Aruco marker has a different pattern. So no matter where the camera is and what orientation the marker is, we get a different pattern. And these different patterns basically help us to estimate the camera pose. So let's start with our NetImplementable detector. Okay. So if we look at our marker, so this is our marker, we can see that this marker has 36 bits in it, or 36 pixels. We can divide the marker into 36 cells or pixels, and using this cell we can calculate what we call the marker signature. It's just going to be a list of 36 integers, being either 0 or 1, depending on the value of the pixel here. So for example, for this orientation, the signature of this marker is going to be like 8 zeros, then 1 1 1 0 0 1 0 0 0, etc. So we can generate different markers with different amount of with different number of bits in the marker. Let's look again about our camera frame and discuss in general what the algorithm is going to be. So we want to detect this marker. So the first thing that we will need to do is to find any squares that we have in the image, and we are going to put this square in the image as well to confuse us. So first we are going to find all the squares in the image, and in order to find squares we are going to use the findContours method of OpenCV. After we find all the squares, so the squares are basically our Aruco marker candidates, we are going to crop and straighten the image around the detected contour, and then we are going to calculate the signature of the square. It doesn't matter if it's a real marker or not a real marker, we can calculate some signature for the detected square, and then we'll compare this signature to a list of predefined signatures that we know that are valid for our marker, and if we have a match, we found the marker. So with that, let's look at the code. I already have the code here. It's mostly commented. We will uncomment the code as we go along. So here we have a loop, the camera loop. We just read frames from the camera, convert to grayscale, and call to the detector Aruco's function. The detector Aruco's function says the first step is to find all the squares on the image. This will be our list of Aruco candidates. So let's look at the find square method. So this is our find square method, and as we said, we are going to find squares using the findContours method of OpenCV. Now basically findContours just find blobs in the image. So the input to the findContours method should be a binarized image, an image of only black and white. So in order to get a binarized image, we use the threshold method. this threshold method basically takes an input image, output image, takes some threshold value. Here we use 100, and for every pixel that whose value is above 100, it's going to turn to white pixel. Anything that below 100 is going to turn into a 0. Is going to turn into to 0. This is how this method binarizes the image. So let's see the result. So this is our camera feed, and this is the binarized image. So we can see our marker, and we can see our other square. But now if I come with my hand, so you can see in the camera feed that I'm not hiding the marker. I just have some shadow over the marker, and this shadow creates this entire environment to be dark, and it all turns into black. So you can say that maybe the value of 100 is not a good value. Let's use a lower value of 50, then we can handle the shade. But when we use 50, we can see now that most of the marker is being transformed into white pixels. So indeed, when I have shadow over the marker, we get the marker, but when we don't have shadow, the marker is gone. So the conclusion from this step is that we cannot use a single value to threshold the entire image. We cannot do what is called the global thresholding. So global thresholding, no good. We are going to use the adaptive threshold. So the way adaptive threshold work is instead using a single value to threshold the entire image. It's going to go pixel by pixel, and for each pixel it's going to look at the neighborhood of this pixel. Looking in the neighborhood, we are going to calculate some threshold value that is localized to this area, and this is the value that we are going to do the threshold with. So the parameters is the input image, the output image, the maximum value that we want. So this is the value of white that is represented. So if you want to binarize the image and you don't want to take the pixels to 255 as white, you can use any other value. This is the method in which we want to calculate the threshold value in the neighborhood of the pixel. So here I'm just using the mean, the average. There is another method that uses the Gaussian distribution. This is the mode of the threshold. This is we do a binary threshold. 11. This is the block size or the neighborhood size that we will use to calculate the average value for each pixel. And this is 5 is just some constant that is going to be subtracted from the mean in order to get the final threshold value. So for example, if for our pixel we look at the 11 pixels around our target pixel, we calculate a threshold value of 20, so we are going to subtract 5 from 20, and the actual threshold value to run a threshold on this pixel will be 15. Okay, so this is adaptive threshold, and let's see the result. Okay, so we still got our marker here, and now you can see that if I have shadow over the marker, it doesn't affect the threshold at all, because the threshold value is calculated taking the surrounding into account. So good. So we got a binarized image, and now we can run findContours. Now, one important property of findContours, findContours actually find white blobs over a black background. And what we have here, we want to detect actually the black blob over a white background. So before feeding this image into the findContours, we are going to flip the image. So we just take the threshold image, and we using bitwise node, we flip the pixels. This is going to be our output contours. Basically, it's just a vector of polygons, and then we call findContour. So the contours gets the input image, the output contours, and this is how we want to get the result as a list of contours. Then we can draw the contours. So I'm drawing the contours using the red value RGB, and I'm drawing the contours on our binarized image, which is grayscale. So before the drawing, I'm going to convert the image to RGB. This is just for presentation purposes. So let's see what contours do we get. Okay, so you can see all the contours that we get. Basically, it's just this is just white blobs that we have in the image. So now we can see that we found our contour here, but besides the outer edge of our contour, we also got some inner contours of our of the marker pattern. So let's see if we can get rid of that. And luckily, the findContours return contours in a hierarchical structure. So instead of asking to get all the contours in a list, we can tell OpenCV, please return the contours, please return only the external contours. So now our marker, we are going to get only one contour for our marker, as you can see, and this SanDisk memory card also got recognized as a single contour. Of course, we have other contours. So what we are going to do now is we want to do two things. One, we want to get rid of all the small contours that are not relevant. And then we want to start to recognize if a contour is actually a square. Now, if you look at our marker here and the contour that surrounds the marker, you can see that it's not built from straight lines. Basically, the contour just follows the pixels, like pixel by pixel. It doesn't construct lines. So we want to take the polygon of our contour, and we want to simplify it and see if we can turn it into just 4 lines to represent the square. So that's what we'll try to do now. We no longer need to draw the contours. Let's uncomment this code. So here we are just looping over all the contours that we found, and now we are calling to the Approx Polydp method. So this is a polygon approximation method, and what approximation polygon method does is basically tries to take a polygon and represent the same polygon like in a simple in a simpler way. So what it does, it starts to remove vertices from the polygon, and after it removes some vertex from the polygon, it compares the new polygon that it got with the original polygon. If the difference between the two polygons is below some epsilon value, it continues to remove the vertices from the polygons until the difference between the two polygons is below the epsilon value. Then it stops. Now, this is what the Approx Polydp does. So we give it an input contour. It's going to simplify the polygon and put the simplified polygon inside this contour CNT object, and this value is going to be our epsilon. So we can think when it compares the new simplified polygon with the original polygon, it's something like it compares the perimeter of the polygons. So we will use the epsilon value as a percentage value from the polygon perimeter or arc length. Okay, so arc length returns the contour perimeter. So if the difference between the simplified and the original polygon is below 5%, so this function will continue to simplify the polygon, and then we will get the result into our contour object here. So for a minute, let's comment this code, and we'll take this contour simplified polygon, we push it to our candidate array, and then I'm going to draw the candidates array. Now, draw contours float. This is a helper method that I wrote to draw contours that are built from floating points like point 2f. OpenCV draw contours method can't handle vectors of point 2f. So let's run this method. And as you can see now, if you look at our polygon, so you can see that it clearly consists from straight lines only. And now we can check, we can go over all the contours and check if the contour is built for only 4 lines, from only 4 points. We know that this is a square, and also we need to get rid of all the small ones. So this is the fifth. We check if the contour size, the contour is just a list of points. If we don't have 4 points, so obviously it can't be a square. And we also can use the OpenCV method to calculate the contour area. If the contour area is below 200, we want to filter these contours. Now I just picked the value 200. It fits my case. You should check for your case. I think it basically depends on the image resolution and how big or small you expect your markers to be in the image. So as you can see now, we get only the contours that have 4 points in them. Okay, if I put this pen here, so you can see that now this pen creates some polygons, some contours that also consist from 4 points, but they are not square. So let's see if we can filter these polygons as well. So we can use the OpenCV method that checks the contour convexity, and basically if a contour is not convex, we know that it can't be a square. Now, without getting into the scientific definition of convexity, let's take a look at these two contours that we have here. So a convex contour or shape, it's a shape that if we take any 2 points inside the shape and we draw a line, the layer will be entirely inside the shape. So no matter what 2 points I choose inside this shape, the line will always be inside the shape. As opposed to a non-convex shape like this, that if I choose this point and if I choose this point and I draw a line between this point or between these points, so you can see that part of the line is outside the shape. So this is not a convex shape, this is a convex shape. So our boomerang that we have in the image, this is a not convex shape, but any square that we find in the image is a convex shape. So any contour that is not convex, we filter, and let's look what we get now. So you can see that we get only the squares. If I put the pen now, I don't get any of the boomerang contours at all. Okay, so we are left just with the squares in the image. The next thing that we can try and do after we approximated the polygons, sometimes the corners will not be exactly at the edge of the marker. So there is a method in OpenCV that calls cornerSubPix. This is an algorithm that tries to refine the corners of a contour. So you give it an image, a grayscale image, you give it a contour, and then this is an iterative algorithm that tries to move the corners to a better location. And for each corner, it uses some window size in order to look in this neighborhood for a better corner. Now note that this window size is actually half of the side length of the search window. So if we give 5, 5, the actual search window will be 10 by 10, or I guess it probably be 11, 11. And because it's an iterative algorithm, we need some termination criteria. So the termination criteria that we are going to define is going to be consisted from two parts. One is an epsilon value, the other is the maximum iteration. So the epsilon value is going to be 0.001. So on each step, it's going to move the corner to like a better position. And if it moved less than 0.001, the algorithm will stop. Another criteria is the maximum iteration, so no more than 40 iterations. So this is sort of like a gradient descent. So this is cornerSubPixels. Now we got a fairly good recognition, so I don't know if we can see the difference with and without the cornerSubPix, but this is the cornerSubPix. Sometimes, by the way, it doesn't work so well, and the corner can jump to like not related position. So you can check if you want to use it or not. Now, once we got the contour corners, we want to make sure that the order of the corners is always consistent and in the same in the same orientation or in the same direction. So we want our contour to start in the top left corner and go clockwise. So in order to visualize it, let's draw a circle around the contour corners, and we're going to start with red, green, blue, and yellow. So let's see what we get. Okay, so we can see that the top left corner is the first one. This is red, but then it goes to green, blue, and yellow. So we want the direction to be clockwise, and this is going counterclockwise. And if we change a little bit our contour, we can see that now the red, the first corner that we get, is actually the top right and not top left. And also it goes counterclockwise. So if you read about the findContours algorithm, you will see that it is guaranteed that the direction of the contours will be counterclockwise, but the first contour is not guaranteed to be the top left. Actually, this is a scanning algorithm, I believe, so the first pixel that it encounters is actually the first. So here the top right corner is higher than the top left, so this is the first corner. And now the top left corner is higher than the top right corner, so this is the first. So we need to reorder our corners. So we have two options. One option that we can get is that the first corner is indeed the top left, and then all we have to do is just swap the green and the yellow in order to have the direction going from clockwise from RGB and yellow. The other option is the top right corner is actually the first corner that we get, and then we have to do two swaps. One is to swap the red and the green, and then to swap the yellow and the blue. And this is our order contour function here. It's a very simple function. I calculate the center of the image, and then I check the first corner that we got. If it's the top left corner, I just swap the diagonals. If it's the top right corner, I swap the bottom and top edges. That's it. And now let's just make sure that it works. So yeah, we got the red is the top left corner, and then it goes clockwise. And now if we change, the red is still the top left corner, and it's going clockwise again. Red, green, blue, yellow. Okay, so the order of the contour will be consistent. So we don't need this, and that's it basically. We are done with the find squares method, and this is a big milestone in our detect Aruco's algorithm. We don't need this. We don't need this. So we got all the candidates 4 markers in the image. Now we need to check if this is actually a valid contour. So we iterate over all the candidates, and we take a candidate, and now we are going to check the signature of this contour. And for this we have the getContourBits function. And the best way to explain this method is actually by debugging, because I added some explanatory images inside this function. So the getContourBits gets an image. So this is our image. Gets 4 points of contour. So these 4 points represent the contour, a square in our image. And then it gets the number of bits that we expect to have in our marker. This assert just verify that the number of bits actually represent a squared image. And as you remember, we divided our marker into 36 bits or pixels. So this is going to be the pixel length. Okay, so you'll see what I mean by that. So the first thing that we need to do is we need to take this square that we got, and we want to extract and straighten this part of the image. So in order to straighten an image, we are going to use getPerspectiveTransform and warpPerspective. What getPerspectiveTransform does, it's calculating a matrix that converts from one set of points to another set of points. So our source points are the points of the contour. So we have these 4 points, and we know that we want to get a straightened image. So we define here the 4 corners of the straightened image that we want to get. So we start with the top left corner, which is 0, 0. Then we want our top right corner to be at the number of the marker bit 36, 0. Then the bottom right corner and the bottom left corner. Now it's very important that our destination corner order will be like our source corners order. That's why we wanted to order our contour. So we always start from the top left going clockwise. So we run getPerspectiveTransform, and once we have the transformation matrix, we can call to warpPerspective, give it our image, give it the output image, our transformation matrix, and the destination size of our image. And this is our extracted straightened marker. So we took the marker from here, and we extracted and straightened this marker. And as you can see, the new destination image that we got is actually 36 by 36. So what we can do now, we can, like we did for our marker, we can divide our 36 by 36 image to 36 bits or pixel, and each pixel length is going to be 6 by 6. Then we can sample the center of the pixel to see if it's white or black. But there is only one problem with this. If you look at our marker that we got here, so the whites are not really whites. So how can we tell when we want to sample the marker what is white and what is black? So for that we need to run another thresholding on our image, and this is what we do here. Sorry, oops. I'll run again. I hit F11 instead of F10. So we were here. Okay, so we want to run a threshold, and like at the beginning of the video, when we did a threshold of the image, we didn't know what threshold values to use, and we ended up with adaptive threshold. So here as well, we don't know what threshold value to use. Now, adaptive threshold will not help us in this case because adaptive threshold will take these parts that are really close, like all this black area, and it will turn it into white. It will not turn it into black because the localized threshold value is going to be really low. So we do need to run some global thresholding. But what value to use? So for that we are going to use a special mode of the threshold method, which is the O2 thresholding. The O2 algorithm, basically before running the thresholding, is scanning the image, and then it picks like the best value, so to speak, for to do the threshold for this image. So this is a global thresholding, but before running the threshold, it examines the image and pick like the best value. I guess it's doing it using the brightness distribution or histogram of this image. So if we do the threshold, we can see that here we have the binary result, and indeed it looks really good. Now let's draw a grid over our result. So here is our 6 by 6 grid, and now we can go and sample the value of each pixel in our marker. But before we do this, you can see that here we have white edges, and sometimes, depending on the camera orientation, these white pixels can bleed into adjacent cells. So what we will do, we want to shrink all the white areas of this image. This is called eroding. So we want to erode the image. In order to run the erode, we need to build some structuring element. This is a morphological operation. It needs structuring element. We use a really small, like the smallest possible structuring element of 3 pixels. And now if you look at the binary image, this is before the erode, and this is after the erode. So we just trimmed a little bit all the white areas of our picture. And now we will draw the grid over the new picture, and this looks good enough. So now we have this loop here, and all we do in this loop is just going over the rows and columns of our grid here, and for each cell we calculate the image of the cell, so the y and x position. So this is going to give us the starting position of the cell, and that's why we add the pixel length divided by 2 to take us to the middle, to the center of the cell. So for example, for the first pixel, y is 3, x is 3, so this is something here, like the center of this pixel. Then we are going to move this center to this center, and at each pixel center, we are going to check the value of the color of the pixel or the brightness. If it's below 128, we are going to push 1 into our result array. Otherwise, we are going to push 0 to our result array. And if we see, so our result array is basically the signature of our marker. It starts with 8 zeros because it is all black, and then we have 3 white pixels, and then 2 more black pixels and a white pixel. So this is the 8 black, 3 white, 2 blacks, white, etc. So we have an image that calculates the marker bits. So this is good. And this is what we do here. We found some contour and we calculated the signature of this contour. Now, how do we know if this signature really belongs to our marker? So for that, we need to build some dictionary that will hold the signature of our marker. So here we are loading our marker image. So this is going to be this image, just without the grid, obviously. And then we are calling to the load marker dictionary function. So this is the load marker dictionary function. We give it the marker image. We tell it this marker has 36 bits. and let's see what this function is doing. So again, best would be to debug this image. So we want to build a dictionary of all possible signature for our marker. So what is all possible? We know that our marker can have 4 orientations. So that's why we run 4 times in a loop. And we start with the upright orientation. Now we need to calculate the signature for this orientation, and we already have a function that knows how to calculate the signature of a marker. This is the getContourBits. It just needs to get an image and the contour of a contour that represent some marker or square in the image. So we know that for this image, the entire image is actually the contour. So we just build here a dummy contour, start from the top left and going to the top right. So the top right is just the width of the image for X and 0 for Y. And then we go to the bottom right and bottom left corners. So having an image with a marker, having the contour that represent the marker, we can, so it stopped inside the getContourBits function. We can calculate the signature for the marker in the upright position, and this is the signature. So we take our signature and we push it to our result signature array. If we look at the result for a second, so it's an Aruco dictionary struct, and this struct will contain 2 arrays. One array hold all the signatures, and the other array will hold what we call the word location of the marker. We'll get to it. So we calculated the signature, we save it to our result. Ignore the word stuff. Now we are taking our marker image, we rotate it 90-degree clockwise, and then we go again here, we calculate the signature for this orientation, we rotate the image, and we calculate the signature as well, and for the last time we rotate for the last orientation, and we calculate the signature for this orientation. So by the end of this process, if we look at our result dictionary, we have 4 signatures, 1 for each orientation. Okay, so this is for the signatures. Now let's talk about what is the world corners, what is the world points here. So for this, let's take this image. So in this image I have 2 markers. One marker is in the, as you can see, in the upright position, and the other marker I actually rotated this marker 90 degrees clockwise. Okay, so let's look at the corners of our marker. So the top left corner of our marker is marked with red, and the top right corner with green, the bottom right with blue, and the bottom left with yellow. Now here it's important to note that I'm talking about the corner of the marker, not of the contour. So when we rotate our marker 90-degree clockwise, this is the top left corner of the marker. Okay, it's like we took the camera to another position. So the top left marker, the top left corner of the marker is still this. It happens that now this is the top right corner of the contour. Okay, so we differentiate between the contour corners and the marker corners. So the marker corners is what we call the world location. Okay, so it doesn't matter if the marker is rotated. Its top right corner right here, the green one, is always going to be the top right corner of the marker. But as for the contour that represent this marker, it's going to be now the bottom right corner. Okay, so having this world location, saving it for each orientation, this would help us to do the camera pose estimation later. This is how we can translate our contour corners to the actual position or orientation of our marker. And this is what we are doing here when we are building the dictionary. So we have the world location, that the initial world location that is defined for the upright position of the marker. So in the upright position of the marker, the contour corners and the marker corners are the same. So we start at the top left. We ignore the z value. Okay, so this is x, y, z. So the top left is 0, 0, and this is the top right corner of our marker. So I chose x25 and y0, and the reason I did this, so this is our top right corner. The reason I chose x25 is because my marker here that I printed, so the length of the marker is 25 millimeters. That's why I chose 25. But it doesn't really matter. You can choose whatever value that you want. You can just use 0 and 1. You can use 100. It doesn't really matter. It will matter later when you want to position stuff relative to the marker. So it like define the scale. So I just decided to go with the size of the marker in millimeters. And this is the bottom right corner, and this is the bottom left corner. So when we are building the dictionary, so we're starting with the upright position. So we calculate the signature for the upright position, and then we take the world location for the upright position, and we push it into the world log of our result. So if we look at our result dictionary, we have one signature that represents the upright position, and we have one world location that represents the upright position of the marker. Okay, now we are rotating the image 90-degree clockwise, and what we do here, we are also rotating the world location. And the way we rotate the world location, we just take the last value and we move it to be the first value. Okay, so when we rotate the marker 90-degree clockwise, so we take this is the last corner in the array. So the bottom left corner, after we do the rotation, it becomes the first corner. So here we take the last corner and we push it, insert it to the beginning of the array, and we insert, after we insert a new value for the world array, we have 5 elements, we need only 4, so we remove the last one that we pushed to the beginning. So in order to rotate the world orientation, essentially what we did is like shift right in a cyclical manner. So now we calculate the signature for the rotated marker, and we push it to our signature result. And we also take now the world location. This is the rotated world location, and we push it to the result as well. So what we have now, we have two signatures for the two orientations, and we have two world location. So the second world location basically tells us that the marker is rotated, because the first corner of the marker is actually the bottom left corner. And this what tells us, hey, in this orientation, know that the marker is rotated. And we continue, we rotate the image, we rotate the world location, and we continue to add this to our dictionary. So the end result, here we have 4 signatures for the 4 orientations, and for each orientation we have the marker corners that actually tells us what is the orientation of the marker. Okay, so we built a dictionary, and now that we have a dictionary, we can actually pass this dictionary to the detect Aruco function. So we'll go to the detect Aruco. we get the dictionary, and here, once we found some marker candidate, some contour in the image, we calculate the signature for this contour. Then we iterate over all the signatures in the dictionary, and we check if the signature that we found matches the signature in the dictionary. And this is the equal signature function. It's a very simple function. You just iterate over the signature and check if the bit in signature 1 equals the bit in signature 2 for the ice location. If they are not the same, we are increasing the misses value. And after we iterated over all the values, we check if the number of misses is below the number of allowed misses, we return true. The two signatures are equal, otherwise false. So this is what we do here. We check if the signature of the contour that we found in the image matches the dictionary signature, taking into account the amount of allowed misses. If we found a match, we said, okay, we have an Aruco. We found an Aruco. Let's push it to our result array. So each Aruco result consists of corners, the corners in the image of this marker, which is just the contour, and the index in the dictionary that this marker represents. We push it back, and finally we return the result with all the Arucos that we found in the image. This is our method. So let's run it. The number of misses, let's set it to 0. Here I have a function to draw the Arucos, so we can see what we find. And yeah, we found a single marker, and this is the 0 index in the dictionary. If you rotate it, index 1, index 2, index 3, we can add another marker in index 0. We can add our SanDisk square. So we know that it was detected as a square, but it's not detected as a marker. We can remove it, and we have another marker here. So this is a valid marker. I just took one pixel of the marker and painted it black, so it's not detected as a valid marker. But we have these misses. So if we allow one miss in the signature, so we say, okay, if the signatures matches, but only one with one miss, so let's consider it as a match. So you see that now it also detects this this marker. So you have some freedom there with the how strict you want to be with the detection of the markers. Okay, so that's nice. We found the markers. Now let's see what we can do in terms of pose estimation of the camera. So for this, we have the draw axis with pose. In this method, we are going to draw the marker axis, like x-axis, y-axis, and z-axis. So first we define the axis points, and now we want to draw the axis on the marker. So now we have to work in the market coordinate space. Okay, so again, if we go back to our paint here, so this is our marker, and what we want to draw like the x-axis. So how can we draw the x-axis? We know that we want to start from the top left corner of the marker. So this is the 0, 0 point of the marker. And we know that our marker, we defined the marker as having a length of 25. So we know that this point is 25, 0. And if we want to draw the y-axis going downward, so we start again with the origin at 0, 0, and this point is x is 0 and y is 25. Okay, so it's important to know that the drawing is actually going to be relative to the marker. That's why we need to use the marker coordinate space. And this is what we define here. We define 4 points to represent the 4 points of the marker that we want to draw at. So 0, 0, 0, it's the origin. This is for the x-axis, this is for the y-axis, and for the z-axis we want to draw upwards. That's why we do minus 25. So we define this axis, and now we want to draw on the image. So we need to convert the points from the marker coordinate system to the image coordinate system. For this we have to get the camera orientation or pose of the pose of the camera, and this is what solvPNP does. So solvPNP takes 2 sets of points in 2 different coordinate systems, and using some calculation it calculates the rotation and the translation of the camera between these 2 sets. So this is the detected Aruco corners. Okay, so this is going to hold our contour values. So it's going to have 4 values starting from the top left to the top right, so in this order, and this is going to be in the image coordinate system, and we want to map these 4 points from the image coordinate system to the Aruco coordinate system. And this is why it's important to know that what index in the dictionary this contour represent. So we want to map it to the world location of the relevant orientation of the marker. So for example, we are looking at this marker which is rotated. So what we tell to solvPNP, we tell that the first point of the contour, this is the first point on the contour, is actually the bottom left corner of the marker, and the next corner of the contour is actually the top left corner of the marker. Now, by having this mapping, solvPNP will know to estimate the pose of the camera to know that the camera is rotated, or the marker is rotated. It's the same. So this is what this function does. And the output of this function is a rotation and translation matrices of the camera. Now, this function also needs to get some parameters about the camera, specifically the camera matrix and the camera distortion vector. The camera distortion is just values about the distortion of your camera lens. And now I don't know the distortion of my camera, so I just uses all zeros. And the camera matrix is also parameters about the focal length of the camera and the center location of the sensor of the image. Again, I don't know these values about my camera, so I just used this value. It doesn't, at the end, it doesn't really matter for our case. It matters if we want to have the correct scaling in the image, like to measure distance. So I don't know the values, I just use this. You can Google and read about camera calibration using OpenCV. There is a process to calibrate your camera, and the output of the process will be the actual camera matrix and camera distortion. So if you want, you can do it, but it's not really necessary for our case. So we call solvPNP, we get the rotation and translation vectors. Once we have this rotation and translation vectors, we can project points. So how we project points? We project points from the marker coordinate system to the image coordinate system. So if we want to draw a line on the marker from the top left of the marker to the top right of the marker, okay, so what project points will do, we'll give it a point 0, 0 in the marker coordinate space, and it will return the location of this point in the image. So I don't know, in the image it's going to be like 500 over 170 or whatever. So it translates between the marker coordinate system and the image coordinate system. And what's important is that once we have the camera pose, our world is always relative to the marker. So the origin of the marker, the top left corner of the marker, either here or here, this is going to be the origin of our coordinate system. And if we want to draw a line from here to here, we need to find the image location of these 2 points. And we know the location on the marker. We know that this is 0, 0, and we know that on the marker this is 25, 0. Or if we want to draw a line from here, I don't know, to here, we know that it's starting from 0, 0, and we go all the way to 0, and I don't know, say 50. Okay, so the project points method will take this 0, 50 point, which is in the coordinate system of the marker, and will convert it to the coordinate system of the image. So we take our axis point in the marker coordinate system, and we get the image, the respective point in the image coordinate system, and then we can just draw a line on the image using the image points. That's all we do. We draw the x-axis, the y-axis, and the z-axis. And I talked a lot, so let's see what's the result. Okay, so as you can see, we got the axis of our exactly on our marker. We can get closer to the marker. We can come from behind the marker, and you see it doesn't matter where the camera is. The axis always attached to the top left corner of the marker. Okay, not the top left corner of the contour that represent this marker in the image. We can add our other marker here, and see it's always attached to the top left corner of the marker. Now, as I said earlier, we can draw whenever we want on the image. We don't have to draw on the marker. So let's say now that I want to draw a square below the marker. So I identified the marker and I want to position something below the marker. Okay, so let's define the 4 points of our square. So we will start at position 0, x is 0, y is 30. So like this is this position. We know that this is 25, so let's say that this is 30. And then our top right is going to be x is going to be 50 and y 30. So we know that this is x 25, so I guess that this is x 50. And then our bottom right corner is going to be x is going to be 50, y is going to be 80. So this is this point, and then we also have the bottom left corner. So we just took 4 points on our image, but relative to the marker. So these points are in the marker coordinate system. This is also called the world. It's in the world coordinate system. And then we project these 4 points to the image points, and using the image points we actually draw the lines on the image. And let's see what we get. So we get now both the XYZ axis, and we also get this square, and this square is positioned below the marker. And you see, no matter where I move the camera, the square is always below the marker, like really below the marker. So the bottom of the marker is always the same, no matter how the camera is positioned, and we always draw the square below the marker. So this is nice, and this also concludes our tutorial, which turned out to be very long. Sorry for this, but I hope I was able to explain this this interesting matter. Thank you. Bye bye.